All right, let's do the following example. We have a 2 kilogram block that's resting on an 8 kilogram block, and we're applying a force on the top block so that both objects move. Now what we're given is there's friction between the two blocks, but there's no friction between the bottom block and the surface it rests on. And so what we want to do is find the acceleration of each object. So the first thing I'm going to do is draw a free body diagram on each object. And so I'm going to draw the top object. I'm going to call this object 1. It's 2 kilograms. I'm not being careful with sig figs here. Let's look at what's touching that object. Well, there's the 10 Newton force. Right? Anything touching the object exerts a force on it. So you have a 10 Newton force. You have a force that's holding that block up. The force that the bottom block exerts on the top block, that's a normal force. I'm going to call it N1. And in general, any surface exerts two forces on an object. One is the normal force and the other one's friction. So if I push on this object to the right, then friction is going to want to slow it down in this case. And so it's to the left. And remember, this is our kinetic friction because they're sliding relative to each other. And then the non-contact force we have is gravity. The other object, the big object, we'll call object 2. It's 8 kilograms. And we want to draw the free body diagram on that one. The question is, what's touching that object? What are the contact forces? Well, okay, there's a surface that's holding this up. That's a normal force. The question is now, what's making this thing move to the right? Well, the force that's making this to the right is actually the friction, the force of friction between these two. If the force of friction is to the left on this object, according to Newton's third law, this has to be to the right. These are equal and opposite. They're action-reaction pairs because this is the frictional force that the 8 kilogram object exerts on the 2 kilogram object. This is the frictional force that the 2 kilogram object exerts on the 8 kilogram object. So they're action-reaction pairs. They have to be equal in magnitude, but opposite in direction. Those are our two contact forces, and our one non-contact force is gravity. Okay, so because they're sliding relative to each other, they are moving independent of each other, so they're going to have different accelerations. If I look at this object, this is what's causing the acceleration. Okay? So really all I need to know is I just need to figure out what the characteristic of this frictional force is. Okay? Of course, in order for me to figure that out, I got to remember that the force of friction, the force of kinetic friction, is mu sub k. Remember, this is a number. This is a dimensionless constant, which relates the force of friction with the normal force. So this has no units on it. It's just a number. And that number, that value, depends on the two surfaces that are interacting with each other. And it's measured empirically. It's measured experimentally. Okay, let's sum the forces acting on this object. Let's sum the forces in the x direction on object 1. We have the 10 Newton force to the right, and then the force of kinetic friction to the left, and according to Newton's second law, it's equal to ma. Now, because this depends on the normal force, I have to figure out the normal force. And so that means I have to sum the forces in the y direction on this object. So up is positive, down is negative. And I didn't say it earlier, to the right's positive, to the left is negative. I have N1 pointing up, M1G pointing down. The sum of those forces equals 0 because it ain't moving up or down. And so the normal force is M1G. And I should label this N1. Okay, let's take a look at this object. If we sum the forces in the x direction on this object, we only have one force. It's the force of kinetic friction. That's equal to m2a. And really, the thing I have to realize is these accelerations are different. So I need to have subscripts or labels to let us know that they are different, because they're moving relative to each other. Well, this is actually pretty nice. It's actually pretty easy because the force of friction is u times the normal force. What normal force? Well, it's this normal force, which is mg. And so A2 is easy to calculate. And I just plug in the values. M1 is 2 kilograms. M2 is 8. Trying to save space here. And G is 9.8. You can punch these in on the calculator. And you get 0.75 meters per second squared. Notice I didn't even need to sum the forces in the y direction on here. That's because there's no motion in the y direction. Now, I do have a mistake here. There is a mistake in this problem. Can you think of what my mistake is? I'm missing a force. It's not going to play a role in the answer, but I am missing a force. I'm missing a force on this one. What is that force? Well, let's take a look. Question I asked was, what's touching this object? Well, this object is on top of this object, right? M1 is on top of M2. This is the force. This is the force of the bottom object and the top object. The reaction to that is the force of the top object on the bottom object. So that has to be there. So that was a mistake on my part. I forgot to put that in. Luckily, I caught that. Okay. So it doesn't play a role in this problem because there's there's no friction between the 8 kilogram object and the horizontal surface. Okay. If there was friction and I needed to figure this out, then N2, if you sum the forces in the y direction, I would have N2 minus M2G minus N1 equals 0. And so N1 is M1G, so I'll write it up here. N2 is equal to M1 plus M2 times G. And friction played a role in this problem, I'd have to account for that. Okay, I need to figure that out, but I didn't need to in this problem. So that was my mistake. I forgot to put this in. Okay, so N1 is there because, well, the top object is touching the bottom object. Okay, don't call that M1G. Okay, don't call this force M1G because it's not. When you do that, you're putting a value on that force. If this system wasn't an elevator, this force would not be M1G, it'd be something else. Right? If the elevator was accelerating upward or downward, this would not be M1G, it would be some value that depended on the acceleration of the elevator. Okay. Now, let's go back to this one. Now that we've figured out the acceleration and accounted for my mistake, let's go back over here. I need to erase my board because all the space I have. All right, so this, we can substitute into here our mu times the normal force. And then we can solve for A1 by dividing both sides by M1. And then I substitute the values. Mu sub k is 0.3, M1 is 2 kilograms, G is 9.80, and M1 is again 2 kilograms. When you substitute the values, you get 2.06 meters per second squared. Okay, so we have everything we need to know for this one, and then for the other one, and like I said earlier, I didn't have to figure out the normal force that the bottom surface exerts on it because really the frictional force, because the frictional force is 0 on it. Okay, so if you wanted to complicate the problem, then you can actually add friction between the bottom surface and the 8 kilogram object. And what that would do is just throw another force in your free body diagram in the x direction on the bottom object. And then you would also have to correctly determine N2 like I did earlier. All right, that's it then.